A little background information about me. I'm a principal engineer at HSBC, and for the past few years, I've been working on designing and building a highly secure, cybersecurity-focused advanced analytics environment within Azure for processing, correlating, analyzing, and reporting on a variety of logs and event streams from hundreds of data sources. I live in Seattle, Washington, but support a global team of engineers and analysts headquartered in London, but spread across almost every time zone. Before spending several years doing multidisciplined cybersecurity work, when my hair was shorter, I was a communications officer in the US Air Force. But for the past 10 or so years, I've been building both on-premises and cloud-based big data cybersecurity data lakes and warehouses. First, I'm going to try to explain some of the challenges we faced, along with a very high-level overview of how we are solving these. We'll briefly go over data mesh architecture, and then dig into some more detailed examples with a little bit of code. I'll try to go through the background context quickly and save some time for questions at the end. Many people in the United States might not realize how large HSBC really is. I had no idea until I considered going to work there. From a cybersecurity perspective, we are monitoring and enforcing security controls on hundreds of thousands of employees with millions of devices on networks across many regional data centers, along with a significant presence on at least 4 separate cloud providers. Our cybersecurity monitoring tools alone generate between 100 to 200 terabytes of data daily that we need to be able to store, process, analyze, correlate, and report on. Some examples of data sources we utilize: NetFlow, proxy, endpoint detection and response, antivirus, firewall, DNS, DHCP, DLP, syslog, cloud environment logs, API feeds from dozens of security vendor portals, output from malware detonation environments, malware repositories, etc. Working with cybersecurity data can be more challenging than other types of business data. Business data is often located in some database somewhere, or perhaps worst case is a CSV extract from some system, maybe even a mainframe. But even if there is not good documentation, there's at least a table schema definition, and usually some team somewhere within the company with tribal knowledge about the history of that data source and the meaning or use of the included fields. Cybersecurity data usually has some sort of structure to it, but it's highly variable. If you're lucky enough to get a JSON extract, you can generally expect that new fields will probably just show up randomly at some point in the future. Or maybe they decided to wrap the entire 500 gigabyte extract as a single line array of record elements. Good luck getting any sort of data dictionary, and if something does exist, it's probably old and outdated. Trying to get answers from the vendor support team is usually an exercise in frustration, with the time better spent simply reverse engineering the data yourself to see if you can figure out if it is even helpful. Most cyber analysts can't know what they are looking for until they find it, as they are searching for an unknown needle in a haystack. So the general requirement for any data request is, give me everything. This is a familiar story for most cybersecurity analysts. Alerts from various systems are sent to a security information and event management system, where a security operations center analyst has to review the alert and then dive into one or more different data silos or vendor portals, often using a separate computer that has an unrestricted external web access, to search for the context and other detailed information around that alert, forcing the unfortunate analyst into a daily game of copy-paste swivel chair analytics that is virtually impossible to automate. Storing data within a SIEM tends to be very expensive, so there's always the consideration of whether that piece of context is really valuable enough to be stored and how long it can be retained. Even if all of the needed data sources have been loaded, it's usually not possible to join data sources with billions of records each within the SIEM. These systems typically make it fairly easy to get data into them, but trying to extract all of it back out is usually not an option. And if the data is stored in the SIEM, there's a good chance that may be the only copy of it. This is what we wanted instead: the ability to ingest and process all of the data, preserve it in its original format, and parse it into a standard, easy-to-query structure so that the same data could be consistently used across multiple cybersecurity use cases. Data can automatically be joined and correlated, applying machine learning to identify the anomalous needles in the haystack, forwarding those events to the SIEM as alerts, When the analyst needs to investigate one of those alerts, there's a single workspace they can use to quickly and easily join and analyze all of the data from a single pane of glass. Cybersecurity metrics and reporting dashboards can be built on top of the same data sets that allow cybersecurity CISOs, management, auditors, and engineers to know at a glance the current status, health, and effectiveness of thousands of different security controls. So, how are we going to make all of this happen at a giant, bureaucratic, highly regulated, risk-averse global bank? Start fresh, a new team, and we would need a new environment that could scale quickly enough to meet the rapidly evolving cyber challenges. Cybersecurity is filled with skeptical people. If we can't prove that we can add value, our new team will be no more. We are engineers. Everything must be code. The infrastructure, the data pipelines, the policy, the alerts. For disaster recovery, the environment has to be resilient enough that we can tear it all down and automatically redeploy it, properly configured, into another region. Long before data meshes and lakehouses and big data, there was the information hierarchy, or information pyramid, or DIKW pyramid. It's been called many things, but to us, it was our North Star, guiding the design of our environment architecture. Don't break DIKW was our design mantra. We always keep the original log data. If there's ever any question or concern about whether data has been properly processed or unintentionally altered during transformation, we should always be able to track the lineage of a data element back to the original source file and verify all the transformation code that has been applied. If any critical errors are discovered, we would need the ability to reprocess the data to correct them. Meet the new team. Cybersecurity science and analytics. We secure the bank using data, analytics, and innovation. Who are we? It might be easier to talk about who we are not. We are not a replacement for any of these teams. Does anyone remember the BASF tagline, "We don't make the products you buy, we make the products you buy better"? We're kind of like the cybersecurity version of that. One of the most challenging design requirements for our new environment was that we wanted to be able to operate with zero dependencies on the bank's core network or any services. If the corporate network were ever to be successfully breached or taken offline by ransomware, DDoS attack, or some other catastrophe, the security team and incident responders will need an environment to operate from, to investigate and recover. Do you remember the Facebook internal DNS and BGP outage in October, when engineers were unable to access physical locations because the building door locks relied on the same DNS infrastructure? Not depending on any core services means we will need to run our own Active Directory with separate user accounts, manage and secure end-user laptops. We will be responsible for meeting or exceeding all of the bank's security standards without relying on any of their standard controls. We will have to replace all of those ourselves. Azure has several unique services to help facilitate our objectives. Azure Active Directory with multi-factor authentication by default and privileged identity management, enabling the temporary elevation of access rights when needed. Centrally managed laptops and virtual desktops with extensive patch management, security governance, policy compliance, and reporting tools. As the enterprise adopts non-Azure Microsoft cloud services like M365, Power BI, etc., Azure typically has the best integration options for extracting and collecting that log data. And in cases where those integrations are insufficient, as a Microsoft Azure customer, it's easier to pressure them into providing an adequate solution. I will say that things have matured and improved significantly with Azure compared to when we first started using it. When we first started planning this project, Azure was not even one of our approved cloud providers. The ad hoc estimate we received when we started planning was that it would take at least 1 year to obtain approval for build, and then another 6 months for pattern review after that. As we attempted to obtain the necessary approvals, we discovered there was no clearly defined process for certifying production infrastructure patterns, and found ourselves in a vicious circle of conflicting approval boards, where each board would refuse to approve until the other board had approved first. But that board wouldn't approve unless the other board had already approved. Tough luck. Most people just give up at this point. It was actually easier, but not actually easy, to just create a new, sane, agile approval process, working with security architecture and governance to formalize a multi-stage design review and approval process via a newly formed design working group. This process became the new standard to approve production infrastructure within the cybersecurity environment. I realize that this is a busy slide. I'm going to break it down. This is just a high-level view. Our environment architecture is based off of the Azure Enterprise Cloud Adoption Framework Data Landing Zone architecture. Microsoft now has a lot of good documentation on their website where they cover the core architecture pattern in depth. For our environment, there are management subscriptions that have centralized logging, monitoring, and compliance, connectivity subscriptions with networking and private endpoints, and firewalls, routers, proxies, etc. There are data ingestion staging subscriptions, a subscription for core data lake and core data processing services, and then multiple landing zone subscriptions for each team or discrete use case. The environment utilizes Azure DevOps for version control and CI/CD infrastructure deployments with Terraform. Each landing zone is deployed as an independent pod with its own network, data lake storage, Databricks Workspace, and Azure Virtual Desktop for accessing the environment. Inbound, outbound network access from within the landing zones is highly restricted, mostly blocked. Accessing the environment requires first multi-factor authenticating to an Intune managed laptop secure access workstation, which can then connect as a trusted device to the Azure Virtual Desktop host. From within that virtual desktop, users are able to access the Databricks Workspace, the Azure portal, the local data lake storage within their landing zone, as well as the core data lake. For their data lake architecture, Microsoft uses a raw, enriched, curated naming convention, which loosely aligns to the Databricks bronze, silver, gold model, or data information knowledge in the DIKW pyramid. The collaboration workspace zone is an area that the individual landing zones can use to publish or share data with users in other landing zones. The only difference from the Azure Data Lake storage within the landing zone is that the collaboration zone can be accessed by all landing zones, while the local ADLS is a private data lake that can only be accessed within that particular zone virtual network. All data lake storage accounts have AD groups mapped to the access control list permission for containers and the top-level folders within those containers. Access to any data can thereby be granted or managed on a per data source basis by the central user management team after getting the necessary approval from the data owner. Data ingestion initially lands the data into separate staging subscriptions based on the source of that data. Data coming from the systems on the corporate network, typically databases, network file shares, NetFlow, syslog streams, are published from an on-prem enterprise data bus that uses Kafka and NiFi to publish real-time streams into Azure Event Hub and batch transfers onto blob storage via ExpressRoute. External data is anything that comes from any public network location outside of the bank. Maybe an AWS S3 bucket, or SFTP, or a web API, or some proprietary agent that needs to be run on a virtual machine. Whatever is needed, dedicated infrastructure is deployed within a separate resource group within the external data ingestion subscription. Data from that data source is written into a dedicated blob storage account for that source. None of the data ingest infrastructure has any permissions on or even network access to the core data lake zones or any of the other staged data. This is done to ensure that any compromise of a data ingestion pipeline cannot expose any of the data from the data lake, and the only data that could be at risk would be the recent data associated with the compromised pipeline. Lateral movement should be extremely difficult. Once raw data lands in one of the staging data locations, it will fire a storage event trigger that will kick off an Azure Data Factory job to scan the data and move it from the staging location to the raw lake. Once the data is in the raw lake, it can be picked up and processed by the core Databricks Workspace to run pipelines to load the data into silver and gold tables. Raw data can be automatically delivered directly into the private Azure Data Lake storage within a landing zone for localized use or processing within that zone if needed. Separating the initial ingestion of raw data from the processing of that data helps to troubleshoot and isolate problems, and also helps to avoid data loss due to failure of a complex central system. The data engineers working in Databricks only have to worry about going to a single data lake location to get any data they need. If the central processing jobs fail, the data ingestion jobs should continue to obtain the data. If a data ingestion job fails or stalls and the primary monitoring doesn't detect that, the monitoring process for the core pipelines should provide additional opportunities for detecting issues. I will walk through an example end-to-end data flow in a moment. I've been following these guys for about 10 years now, since before they were Databricks. Ever since Matej Zaharia came to a Seattle Spark meetup to talk about Spark as a Hive execution engine. So for me, they were the most obvious choice. The fact that I have the option to easily deploy the same platform within multiple cloud environments and migrate my core data processing and analytics environment with minimal refactoring or impact to users is a huge plus when trying to avoid being locked into a single cloud provider. But I also really appreciate the fact that my data is also not locked into them. I don't have to use them for any of this. I could have built basically the same architecture using another solution for managing my Spark clusters, still using Delta Lake. My data is stored in a format that I could just start using, reading from with another provider, or even just maintain and deploy the clusters myself. This is why we're so excited to see all of the latest performance features of Delta Lake 2.0, like Z-order optimization and the change data capture feed being committed into open source. But Databricks also listens to their customers. And if they realize that there's a feature that would be helpful to multiple customers, it may magically get added into a future release. When we initially started designing our environment, we weren't trying to create a data mesh. At that point, the term hadn't even been invented. We were, however, familiar with the many common failure modes of traditional centralized data lakes and warehouses, and we were striving for something better. I've already talked about our problems with vendor data silos, and we knew that a monolithic, centrally managed warehouse would be too inflexible for our needs. We were already planning this distributed lakehouse architecture. From an infrastructure architecture perspective, this is really starting to look a lot like a data mesh. When I first showed our environment to Serge from Databricks, he said, "You've built a data mesh." I responded, I guess you could call it that. And he said, no, it's a new architecture. It's like what you have built. However, there are a few areas where our internal process implementation arguably may not purely align with certain aspects of the aspirational data mesh vision. In a highly regulated environment, it is not up to the whims of the user which data they can store in a particular environment. Just because they have access to some data doesn't mean that we have the legal authority to store it within our cloud in a particular region. There is a formal data visa process to review and obtain additional authorization if necessary to host a particular data set. In a data mesh, the owner of the data is supposed to be the group that produces it, but most of the data that is used within our environment comes from some external sources. Who should own those? Data governance is hard and not always a lot of fun. When performed as an additional duty by each individual team, eventually it will inevitably result in an audit finding. Without any central standardization or management of data sources, the same data set will often get processed by different teams in slightly different ways. This consumes both excessive human and compute resources and prevents there from really ever being a single source of truth. These are some of our data product teams. They each have their own dedicated landing zones for their work. As new teams or use cases need to be added, Terraform template patterns can be used to quickly deploy additional zones. A generic view. The core team is focused on initially creating silver delta tables for all new raw sources. Individual teams can then use those silver tables to build gold tables dedicated to their use case. If a team needs a new raw data source loaded more quickly than the core team can do the work, they are able to access the raw data and self-service the entire ETL pipeline within their private data lake if needed. If ETL development is performed in a standard way, that development can be distributed into individual team landing zones, merging the ETL code through a PR review process for CI/CD deployment into a production Databricks workspace running in the core subscription, managed exclusively by Terraform, that is able to write to the core lake. That production workspace is the only workspace with permission to write to the core lake enriched and curated zones. Transformations are executed as individual functions that can be individually unit tested and easily PR reviewed. Each of those functions should return a data frame. Using this approach also makes it very straightforward to convert existing workflows into Delta Live tables pipelines. The standard ETL also includes standard metadata columns like input file name, get commit ID of the ETL code version which loaded each record, the date the record was loaded, etc. These can be used for future data lineage and data quality validation. Since each landing zone has its own Databricks workspace, we need a central way of consistently managing the configuration across all of them. Terraform is great for this, and it can also be used to sync user membership via AD groups, as well as for the deployment of production jobs into the production workspace. Serge Smerton gave an in-depth talk about this yesterday. I highly recommend watching it. Sometimes, things that seem like they should be straightforward turn out to be surprisingly challenging when working in a security-hardened environment. For instance, we initially had some challenges automatically configuring Power BI Desktop to utilize the proxy, but after we had that working, we were still unable to connect Power BI Desktop to our clusters. As it turns out, the Power BI Desktop connector was, until very recently, not itself proxy aware. It took multiple days of troubleshooting to figure this out, and we ultimately had to craft custom firewall rules to permit the traffic. Now, though, this should no longer be an issue. For the next person who thinks this will be straightforward to set up, it actually will be. It should just work. While we were searching for solutions, we realized that for scheduled data refresh dashboards, Power BI could simply read the Delta table directly from ADLS without even using a cluster. Unfortunately, at the moment, this is not a native built-in connector in Power BI that makes this super easy, but it is instead is a Power Query function that needs to be copy-pasted into a Power BI custom data source, adding a little bit of friction to the development process. There is also a custom connector available in the repo that can be added to the local Power BI desktop installation with a little bit of effort to automate that configuration. In this code, the function read Delta table is the Power Query function that needs to be copied from the GitHub repo. This pipeline to collect and ingest our endpoint defense and response logs is one of our larger individual ones and has some interesting aspects to it. This data was invaluable to the team when we were responding to the Log4j vulnerability this past December. Tomorrow morning, my colleagues, Jude and Abigail, are going to be giving a talk about some of their use cases for this data. Each day, the stream contains about 3 terabytes of gzip compressed JSON data, which decompresses to around 30 terabytes of raw data over about 14 billion records. The data is produced in batches of between 5 to 100 gigabytes every 3 to 5 minutes. At the moment, the raw data stream contains about 280 unique event types, and each event type has unique schema fields, with about 2,000 unique fields across all events. New event types and fields might be added at any time. When a batch of data has been written to S3, an SQS message is created with a link to the bucket path. Every 30 seconds, an Azure function is checking for a new SQS message. When one is found, the message is parsed, and the S3 bucket path is passed to another function that starts the download. When the download finishes successfully, a final success file is created, which serves as a trigger for a data factory job that moves the data into the raw lake. As new files land in the raw lake, Autoloader picks them up and streams them into a single text field Delta table partitioned by event type. That data then serves as the source for 280 streaming jobs that populate the individual event tables. This work is split across 3 clusters. The first cluster is doing the majority of the work. It parses the raw stream along with about 30 of the highest volume event table streams. The remaining 250 event streams are all individually fairly low volume, but managing all of those streams can put a lot of pressure on the cluster driver node. Eventually, it may cause instability, and it can take a few extra minutes to initially get all of the streams started when the pipeline restarts. Therefore, all of these lower volume streams are run in the second cluster to minimize the pressure on the driver of the first cluster that is doing the heavy lifting. The third cluster is processing each of the records in the raw table to discover any newly added fields. As new fields are identified, they are added to a reference schema table, and each time either of the first two pipelines is restarted, that table will be queried, and any newly discovered fields or event types will be added to the pipeline automatically. Here we can see the number of records loaded per day. While we were doing some testing work, the upstream ingestion portion of this feed, the lower volume in the middle, is when that was down for a bit, and the subsequent spike from it catching back up. Overall, the core code is not really very complex. There is a lot of conditional edge case handling happening in the apply schema function, which isn't shown here. The main DLT pipeline queries the reference schema table to get all of the event types and the column schema for each event type. The write single event table function then creates a DLT table stream for each event type. Discovering new fields is also very simple using the JSON object keys Spark SQL function. But I was unable to figure out a way to implement the for each batch logic here within a Delta Live tables pipeline, so this is running on a separate job cluster. However, trying to parse the JSON fields using PySpark or Spark SQL was too slow to do complete field schema profiling. To get efficient schema profiling, we had to use a Scala UDF. The code here is a little dense. I'm not going to go through all of it now, but providing it here as a reference. For schema profiling to be effective, a certain minimum number of records needs to be observed. When conducting new field discovery, new fields will inherently be discovered after only a handful of observations. Therefore, all newly discovered fields are added as string type to avoid future schema migration conflicts. A rotated view of the DLT pipeline execution graph so that I could get it to fit on the screen. The one with 250 tables in it would be pointless to try to display here. In addition to the record-level data quality controls that can be defined and enforced within DLT pipelines, we have additional data quality processes to ensure that all data is arriving when expected, getting successfully loaded into Delta tables, and that aggregate record statistics match historical trends and expectations. The data in the raw lake is structured in a time-ordered path structure beneath a top-level folder for each data source. The success file that is created at the end of each stage of every data transfer job is a JSON file that contains metadata about the transfer activity. The metadata contains a list of all of the file paths that were copied during the transfer, so this information can be used to avoid a slow directory listing process on the raw lake when it's time to reconcile whether all source files have been loaded into Delta tables. The metadata from these success files is then processed, analyzed, and presented in a Power BI visualization dashboard that shows the current health, status, and historical volume of every raw data ingestion feed. The next phase of our development will be to correlate the raw file paths with the input file name path metadata collected in the Silver Delta tables to verify that 100% of the data coming into the raw lake is successfully getting loaded into Delta Lake. We are additionally looking at applications of machine learning to help determine when a constantly fluctuating data volume is reasonably expected or some indication of an issue with the data ingestion pipeline or upstream data source. I know that I covered a lot of material here rather quickly. This was about 3 years worth of work in 30 minutes. I'd like to give a few minutes for questions now, but I'd be happy to continue a longer discussion offline, so feel free to reach out. Thank you for your time.
Thanks a lot for the presentation. I want to ask you, since this has been for 3 years, how is it going right now with the data mesh, the different teams, any core challenges you have faced, since you have a bit of experience on that?
So the 3 years ago was when we were starting the design process and working through approvals and all of that. We've been up and operational in some phase for approximately a year now, and maturing our data, processing through all of the backlogged raw files, and starting to build use cases on top of it. And one of those use cases these guys will be talking about tomorrow.
Hey, Ron. Yeah, thanks for the talk. Very informative. I had a question on your reasoning as to why you kind of chose to have a single raw Delta table that you would have your 250 Delta live table streams stemming from. And did you face any challenges with optimization or scalability when tomorrow you want to kind of move that up to like 1,000 streams from a single source?
So it wasn't my choice to pack all of those into a single stream. That's how the raw data gets delivered to me. So I had to come up with a way of splitting that apart. And the way we're doing that is by, on the first phase, when we're reading it in and dropping it into that first table, doing semi-structured JSON querying to get just what we need to identify the event type and using that for partitioning. When we first tried to load the entire stream into a single table, with 2,000 JSON fields wide, most of them sparsely populated, the performance was hell. So being able to split that by partition so that then each event stream can just pop just the files that are related to that, and then everybody uses those event streams for the work.
So the question is, so this looks more as a DIY data lake versus something that you buy off the shelf. Like, were there existing off-the-shelf implementations at HSBC which you replaced eventually?
No, we were building this fresh and new. The previous approaches all relied on analytics based on top of the SIEM, and the SIEM being the source of truth for all of the data. So sure, there were analytics use cases outside of cyber at other places at HSBC, but no suited environment for the type of work we needed to do.
Mainly, what was lacking in the SIEM solution, which you are bringing to the forefront?
Yeah, the cost of ingesting and storing data, and then if you're trying to do large joins, they can do pseudo joins in a SIEM up to 100,000, maybe million records, but you get over that and it's best effort joining. Thank you for your time.